Hey there guys, it's Mr. Sheeline here for the Unit 5.2 Check Your Understandings from the Notes Conservation of Momentum in Collisions in One Dimension. So, okay, let's just get straight to it. Check your understanding. Number one, a vacationer of a mass of 75 kilograms is standing on a stationary raft of 55 kilograms. Vacationer then walks towards one end of the raft at a speed of 2.3 meters per second relative to the water. What are the magnitude and direction of the resulting velocity of the raft relative to the water? We're going to neglect fluid friction between the raft and the water. Before we get into this, let's think about this for a second here. So we've got a guy here in the water, okay, and this guy is in a raft, okay. So we got a guy here standing in a raft, and this guy is going to move from this end to the raft, and we'll say to this end of the raft, okay? And then we've got to think about this, and if you've ever done this before, if you've ever stood up in a canoe or a raft or a boat, like a little, flat bottom, a small little boat, a little rowboat, that once you start moving in one direction, what we should expect is the boat moving in the opposite, okay? That's what we should expect, okay? Think about it for a second here, okay? Because when we are walking on the ground, the thing that's great about walking on the ground is that there's enough friction force between the floor and our shoes or the floor and our feet most of the time to propel us forward while we walk. Now, if we try to do that and apply a force this way on an object, but then, we're walking this way, but realistically speaking, what's the direction of the force here? Well, when we push off the ground, our feet are actually pushing a force in this direction, and that's a foot, by the way. The force is going to be in this direction. Okay, so yeah, our movement's going this way, but we're pushing. We are pushing off the ground to propel us this way, but we're pushing in this direction. So we should expect then that the motion of the boat here is actually going to be opposite to the motion of the person here. It's going to be with the force being applied here. Okay. So let's keep that in mind, and then let's write down our variables. So here we've got the mass of the dude, the vacationer, which is 75 kilograms, mass of the raft, which is 55 kilograms. We have the velocity, and actually we'll say the initial velocity of the vacationer. We got the initial velocity, initial, which is 0, okay? And we also have the initial of the raft as well. Oops, that should be R and then I. That is also 0 meters per second. And then we see that this guy, because it says here that the guy's just standing there, the vacationer is standing on the boat, and then he begins to walk forward. So we have initial and we have then final. Okay, so final is going to be 2.3 meters per second. And then what we're trying to find here is the final velocity for the raft. Okay, we don't know what that is. But we do know that these two don't have a direction. We're going to say, this will be in this direction because of our picture up here. This is going to be opposite to this. Okay. So we've got all of our variables here. Now what? Well, because we're working with conservation of momentum, we know that the momentum in the beginning must be equal to the momentum at the end. So in this case, we're just going to write out our equation, which is going to be mv. I'm just going to keep it to the generic one. Is equal to, I'm going to have to squeeze this guy over here. mv1f plus mv2f. Okay, so we got to use this equation right here. And I wrote this down here because I ran out of room. So we're going to go to another page, and we are going to write out our equation again. mv, but this time with our actual variables. mv, oh my goodness, vi plus mv ri equal to mv vf plus oh my goodness, MVRF, goodness. Okay, now, this is what's really cool, is that if we did not know the direction of the boat, or the direction the boat was going, actually, I won't say anything just yet. We'll hold on to that for a second. So, okay, so we've got our equation here. Now, we understand, though, that, yeah, we've got mass initially, or on our initial side here, but unfortunately, nothing's moving. So we can just get rid of these guys and just replace it with 0. Okay, so it's going to be 0, because that's, initially, that's our momentum. We didn't have movement. There is no velocity, and because we have no velocity, we have no momentum. So we have 0 is equal to mf_vf plus mv_rf. Okay. So we've got this, we have this, but we don't have this. So we've got to find this guy right here. So let's just set it to equal that. Okay, so we're going to move that over, so then it'll be negative mvvf equal to mvrf. And then we're going to divide by the mass, and this will be the mass of the raft. It's the mass of the vacationer. Okay, that cancels out over there. And then we are left with VRF equaling negative mv VVF divided by mr. Okay, and then we're left with this. Okay, so then we are just going to plug in jug. So let's do that. So mass of here is going to be 75, and that's going to be 75 kilograms times the 2.3, and it's going to be all over the mass of 55. Squeeze it in there. Then we do that on our calculator. And then what we find here is 3.13, we'll say, meters per second. Not just that, negative 3.13 meters per second. So even if we didn't know that the boat was going to move in the opposite direction, if we didn't know that before going in, we definitely know now. So it's a negative 3.13 meters per second. So we can either keep it like this, but realistically speaking, what would be better is like this. We would say it's moving at 3.13 meters per second, opposite of the vacationer. Here, just so to emphasize that, this is the answer we got. So it'd be the final velocity of our raft is equal to 3.13 meters per second in that direction. Or you could say just opposite of the guy, okay? So there's check your understanding number 1. Now let's move on to check your understanding number 2. Okay. Get it up here. Okay. So during a football game, and this is an example of, these are going to, the next 3, I think, are going to be examples of completely inelastic collisions. So during a football game, a fullback of a mass of 108 kilograms runs at a speed of 9.1 meters per second to the right. This dude is tackled head-on by a defensive back that has a mass of 91 kilograms, running at a speed of 6.3 meters per second in the completely opposite direction. What is the speed of this pair just after collision? So this is a perfectly or completely inelastic problem here, because what we know is that when you tackle somebody, for the most part in football, when you tackle somebody, you're grabbing them and you're taking them to the ground with you, or at least pushing them forward with you, right? So in this case, we're going to start off with 2 distinct objects, and then we're going to be calculating this with 1 distinct object. So let's write down our variables here first, show what we don't know and what we know. So it looks like we've got the mass of the fullback, so FB is going to be 108 kilograms. We have the mass, and his velocity. And this is going to be initial velocity. Okay, we've got that at 9.1 meters per second, and this way. Then, defensive back with a mass, and this is going to be DB, with a mass of 91 kilograms. This dude is running a pretty quick speed. maybe not as much, but at a decent speed. This is going to be the, let's see, that's going to be 6 point, that's also initial, 6.3 meters per second to right. Oh, opposite direction, my bad, opposite direction. Okay, and what we're going to find is this. We are mainly wanting to know the speed afterwards. So it's going to be speed, I'm going to put t for total, because again, this is going to be the velocity of both the fullback and also the defensive back. So we don't know this, but before we move on, we also know this. We do know the mass of, we'll say the total mass here. Oop, I don't need a line. Ignore that line there. The total mass is going to be the mass of the defensive back and also the fullback. So that's going to be 108. So that's going to be 108 plus the 91 kilograms, which is going to be 199 kilograms. Okay, so that's going to be our total mass here. So our formula then, like what we've been doing since the last one, will be the m of, and I'm going to put the variables in, m of FB times the velocity of the FB initially, plus the mass of the defensive back and the velocity of the defensive back initially is going to be equal to the momentum, the total mass, and also the total final velocity of these two dudes. Okay, so let's now just plug and chug. So we've got the fullback here, sorry, we're not going to plug and chug yet. Let's set it to the velocity here, which is going to be super easy. Okay, MFB VFBI plus MDB VDBI over MT. Okay, oops, I did not have that in. Sorry about that. Did not see that. And that's what we've got so far. So now that we have it set to what we're trying to look for, let's plug in our answers. So that's going to be 108 times 91 or 9.1, sorry, plus the mass of that guy, 1d1 times 6.3. But for now, we're going to establish one of these. Sorry, I almost forgot to mention this. We have to establish one of these as negative. So we're going to specifically associate, because mass isn't a vector quantity, we're going to associate the velocity since it's a vector quantity. We're going to say that this guy right here, because just by looking at it, he has a higher momentum, so we should expect them to continue in this guy's direction. We're going to make this 6.3 a negative because he's moving in the opposite direction of this guy. And then down here, it's going to be the mass of both of them, which we found out is 199. So we're going to calculate all that. So that's going in our calculator. So that's going to be 109 or 108 times 9.1 plus, and that's going to be a 91 times a negative 6.3 divided by, let's just put that in, and then divided by 199, which is going to give us a positive 2.06 meters per second. So since our total came up positive here, our final velocity on our calculator came up positive, knowing that this guy is negative over here, correctly knowing that that's negative here, that tells us that this velocity of the guys, basically, that's now one unit, they're moving positively in the same direction as our fullback, which again we should expect. He has a higher momentum than the defensive back that has a lower momentum trying to tackle him. So, and then we would cap it off by saying they're gonna move in this direction, and we have our answer. Okay. So let's check your understanding number 2. Let's take a look at check your understanding number 3. So an 80 kilogram roller skating grandma collides inelastically with a 40 kilogram kid at a rate of 6 meters per second. What is their velocity after the collision? Okay. Now this one we can do a number of ways. So let's just write down our variables. So we've got the mass of grandma, 80 kilograms, mass of kid, 40 kilograms. And because this is a completely inelastic problem, we know that there's going to be a total mass here because they're going to become one unit. So the total mass here is going to be 120 kilograms. And we need to find what the total, or what the final velocity is at the end here. We are given grandma's velocity initially. Grandma's initial velocity here is going to be, what is that, 6 meters per second? I found that in the picture, and also that's given to us. Whereas the kid's initial velocity is 0. We're going to say grandma's moving in this direction. Okay. And it's going to be 0. So, like I said, we could, what we could do is that we could just use the same equation that we did before in order to find this. And that's pretty much, there's another way I could show you, but I'd rather not confuse you terribly. What you could do is just find the difference in momentum, which is pretty much what we're doing, but it goes a bit differently in route. We're just going to stick with what we've been doing for the last, after this one, 3 problems. Let's just write down our, the initial side and also the final side of our momentum. So the mass of grandma and the initial velocity of grandma plus the mass of the kid times the velocity of the kid initially is going to be equal to the total mass of both of them, and then also the final velocity of both of them as well. Okay, so we already know that we could probably just get rid of this because the kid's not moving. Velocity is going to be 0. He has no momentum. So what we can then do is just cancel that out, and then what we're left with is this. Okay. And then from here, we can then set it to equal this. So then we're going to then divide both sides by the total mass. And then we're left with the total final velocity of these 2 individuals is equal to the initial momentum of grandma here divided by the mass of both of them. Okay. Plug and chug. So then that's going to be the mass of grandma, which is 80, times the velocity of grandma, which is 6, divided by the total mass here, which is 120. Okay. So 80 times 60 divided by 120. What did I do wrong here? Oh, I did 80 times 60. 80 times 6 divided by 120. I got 40. I was like, there's no way are they moving at 40 meters per second. And then because we're moving in the same direction, the kid was just standing there, and we're moving in the same direction, it looks like. Because if we weren't, then, and if we didn't expect to go in the opposite direction, then we would have no momentum at the ending, and we'd have no velocity, which would mean that grandma came to a full stop. But we don't have that. In this case, it seems like we have a positive number here, which means that it's moving in the same direction as grandma, and it's at the rate of 4 meters per second, specifically in this direction. Okay. Cool beans. Okay. Then, that is check your understanding number 3. So then let's go to number 4. Check your understanding number 4 here. A fish moving at a rate of of 2 meters per second swallows a stationary fish, which is a third of its mass. What is the velocity of the big fish after eating his dinner? So let's just write out all of our variables. So we have the mass of the yellow, I'm going to say yellowfish and bluefish. So the yellowfish is the big one, bluefish is the little one. Okay. We're going to say that this guy has a mass of 3m, so just 3 mass. Okay, so that m right there is going to stand for mass, not meters. Whereas the bluefish, the little guy, he just has a mass of 1. Okay, so you could have these opposite, by the way. You could have the yellowfish equaling 1, and you can have the bluefish equaling 1/3, like 1/3 times m. It works the same way. It's just, this is just how I do it. And then let's see here. So the big fish here, the yellowfish, is moving at a rate initially of 2 meters per second. We're going to say he's moving this direction. And then we have the velocity, initial velocity of the blue guy. He ain't moving. Okay? And again, just like we've done for the past 2 problems now, we know that at the end their mass is going to be equal, so or it's going to be totaled here. So in this case, what we have here is the total is just going to be 4m, because it's just 3m plus m, which is 4m. Okay, so now 4 times the mass. Okay. And then we've got the total mass here, and then we also have the, or what we're looking for here is going to be the total final velocity. That's what we're looking for. How quick is this whole thing going to move? Okay. So just like the other ones, we're going to have the mass of the yellowfish times the velocity, the initial velocity of the yellowfish, plus the mass of the bluefish, velocity, initial velocity of the bluefish, which we know is going to be 0, and then total mass of them both, and then the final velocity of them both. So again, cross that guy out because we don't need him. It's going to be 0 because he's not moving. He has no momentum. Okay. So that's going to be my vyi is equal to mt vgf. Again, trying to find this right here. So then we're going to set that equal. My vyi. So then mt. We've got our equation here now. Let's just plug and chug. So this is where it's going to get a little tricky. Okay. Okay. So we're going to have here 3m, because that's what that is right there. Remember, not 3 meters, but just 3 times the mass, times 2 meters per second over 4m. Okay. So what we can do here is just simple algebra. So we know that the m is going to cancel out. Okay, we already know that. The mass is going to cancel out. So what we're left with here is pretty much this. We're left with, we could look at it this way. We could say this is now 3 over 4 times 2. Okay, that's what we could say right now. 3 divided by 4 times 2. Same thing right here. Okay, don't believe me, go try it out. Shoot, if you want to do 2 over 4 times 3, it's going to be the same thing. Okay, so we've got 3 over 4 times 2. So we're going to do that. 0.75, or 3 over 4 times 2. And what we should get here is that the final velocity of the 2 masses here is going to be 1.5 meters per second. Squeeze it in there. In the same direction as our big fish, our big old yellowfish. So to rewrite that, the final velocity of them both is going to be 1.5 meters per second in this direction. Okay. Moving on to check your understanding, number 4, or that was 4, now 5. Whew, bear with me. I know this is a long one. Remember, if you think you've got it, you can just bounce back and forth to each question just to see the answer. You don't need to stick around. If you've got the correct answer, you don't need to stick around and watch this whole thing. So, okay, so check your understanding, number 5. So a 5-gram cart is moving at a rate of 2.0 meters per second on an air track elastically and then elastically strikes a 1,000-gram cart at rest. What are the resulting velocities of the two carts? So just a quick note, this is an elastic problem. So we're going to be using those two little cheater formulas in order to solve for the velocities for both objects here. Because what we have here is we have, cart 1 and we have cart 2, and we've got cart 1 here, which is moving in this direction. This guy is just chilling out, okay? He's at rest. This guy is moving at initial velocity of 2.0 meters per second. This dude, again, is at rest, and we are going to see what their velocities are. Not only are we going to see what their velocities are, we'll get a sense of what their direction is as well, okay? So anyway, so let's get a sense of that, and in order to do that, we need to first identify our variables. So we've got the mass of, we're going to say cart 1, we'll just say mass 1, and it is 500 grams. I'm going to write this out as kilograms because that's what we have to use. That's going to be 0.5 kilograms. This dude is initially moving at 2 meters per second, and we're going to say in this direction. The mass of the second cart is 1,000 grams, or 1 kilogram, and initially it's not moving. Okay, so what we're trying to find here is we're going to try to find, not the M, but we're going to find, because they're not going to stick together. They're not doing that. This is elastic now. It's not inelastic. This is elastic. So they're going to stay separate. They're going to be distinct. So what we're going to find here is the final velocity of our first cart here, and then the final velocity of our second cart right here. Okay. So again, if you want to know the derivation of what I should say, if you want to know how it is that we can find the derivatives, or these derivatives that I'm about to put up, these equations, you can go ahead and ask me at any time. I'll walk you through how it is that we can calculate them. But these are the formulas we're going to use. We're going to use the final velocity of our first object is going to be equal to m1 minus m2 over m1 plus m2 times the initial velocity of our dude here plus 2m2, the 2 times the mass of our second object over m1 plus m2 times the initial velocity. Okay, so real quick, since I've already set this up, I'm just going to solve for this guy. We already know that this is going to be 0 over here because our initial velocity for cart 2 is 0. So we're just left with this. Okay, so I'm going to just plug in. So that's going to be 0.5 minus 1 over 0.5 plus 1 times my initial velocity, which is 2.0 meters per second. Okay. So if I pop that into the calculator, it's going to be 0.5 minus 1 divided by 0.5 plus 1 times 2. So what I'm going to get here is a negative 0.67 meters per second. So because my calculator brings that up as a negative, that means that actually this is going to be 0.67 meters per second in this direction. It's going to hit our cart, and it's now going to move in the opposite direction it was moving. Okay, so first it was going this way, and now it's going to go this way. Okay. So there is the answer for our initial velocity, our final velocity for cart 1. So now let's figure out what the velocity for cart 2 is, the final velocity for cart 2. So we're going to have that, which is going to be equal to 2 times the mass of our first object, all over mass of 1 plus mass of 2, times the initial velocity of our first object, plus, oh boy, going to write this out even though it's going to be 0 anyway, and you should know that. Because it's going to be the initial velocity of our second object. That's 0, so we don't need it. So then we got this. So 2 times m1, which is the mass of our first object, which is 0.5 all over 0.5 plus 1 times the initial velocity of our first cart, which is going to be 2. Okay. So then that's going to be 2 times 0.5 divided by 0.5 plus 1 times 2. So then all that momentum, all that energy is now being transferred to our second object here, which it was sitting at rest, is now going to move at 6 meters per second. And because it's positive, 6 meters per second in the same direction as our first cart when it was initially moving towards the object. Okay? Which, I'm thinking about that now. Did I do something wrong? I don't think that's right. Here, give me a second. Let me figure this out. I don't think that's right. Yeah, that isn't right. I popped in something wrong. Here, give me just a second. Yeah, there we go. I don't know why I got that. Wait a minute. Hold up. Oh yeah, times 2. That's it. Sorry. That's not 6. My bad, because I was going to say, wait a minute, that shouldn't be right. 1.3 meters per second in that direction. My bad. So it's going to be moving in 1.3 meters per second to this in the same direction as cart 1 was before the collision. Okay. Oh boy. What was that? Was that 5 or 6? My goodness, that was 5. We still have 2 more. Okay. Again, patience. Check your understanding number 6. So a ball with a mass of 4 kilograms and a velocity of 5 meters per second collides with a second ball of a mass of 6 kilograms that is moving in the opposite direction with a velocity of negative 5 meters per second. What is the velocity of each ball after the collision? Okay. So mass of ball 1 is 4 kilograms, has a velocity of 5 meters per second. We're going to say in this direction. Mass of ball 2, 6 kilograms, velocity, this is initial. It is also 5 meters per second, but in this direction. So it will be a negative, so keep that in mind. What is the velocity of each ball? So we want to know what's the final velocity for each ball here. So we're going to use those 2 equations we just used. So let's just find the velocity of final velocity of our first ball here. So looking back at our equation, so m1 minus m2 over m1 plus m2. Oh, and by the way, if you're thinking like that you've got to memorize this, don't think you have to memorize this formula. You'll have a cheat sheet for this during tests and quizzes. Don't worry about that. Okay. So now we don't get rid of this guy over here because that guy we actually have a quantity, so we actually have to plug all that in. So let's go ahead and do that. So m1 is going to be, so that's going to be 4 minus, 4 minus 6, and then it's going to be 4 plus 6 times 5 plus 2m2, which is going to be 2 times 6, and then 4 plus 6 on the bottom times 5. So then the initial velocity, once we've got all that figured out, the initial velocity, so 4 minus 6 divided by 10 times 5 plus 2 times, or 6 over 10. Or 12, let's see, 12 over 10. and that's going to give us a velocity of 5.6 meters per second, and it is positive, so, which is very unexpected. I think I did something wrong here. Here, give me a second. This is why it's always good, like if you see something that you're like, or it's always good to just have a guess of what something will look like before you punch it in, like, you know, estimate, make a prediction, so that when you see something that you did not expect, you can go back and say, I need to relook at that. Still. I'm still getting something I'm not expecting here. What am I this is a negative. That's why. I almost forgot. That's a negative. So that's why it's definitely not this. That's a negative. Probably not going to go in that direction. That's a negative specifically because it's moving in the opposite direction as this. That's why. Okay. Oopsie daisies. Let's try that again. So, divided by 10 times 5, negative 1. Oh boy. Just punching it in my calculator and making sure it's all good. Plus negative 5. Okay, maybe we're getting a little closer here. We're going to see if I get a negative 7 meters per second, and it's going to, so it's actually going to be in this direction. So get rid of that. 7 meters per second in the opposite direction that it began with. Okay, so we're going to double check that at the end, so keep that in mind, because I told you that's a great way. So we're going to double check to make sure that the initial momentum is equal to the final momentum. Okay, and then here we're going to find the final velocity of our second object here, which is 2m1, m1 plus m2, and plus m2 minus m1 over m1 plus m2 v2I. Okay. Remember, this is going to be negative. Plug it all in. So 2 times m1, which is 4 over 4 plus 6 times 5 plus m2 minus m1. So that's going to be 4 minus 6 over 4 plus 6 times a negative 5. So 2 times 4 divided by 4 plus 6 times 5 plus 4 minus 6 divided by 4 plus 6 times negative 5. Huh. Also very unexpected. Here's what I got. 5 meters per second. It's a positive. Oh, yeah. Interesting. Again, I did not it's been a while since I've done this problem, so this is, I guess, without looking at my key, this is unexpected. This is what I get, is 5 meters per second. Let me double check. So 2 times 4 is 8 plus 10, so that's 8 over 10 times 5, which is 4. Then this over here is negative, it's negative 2 over 10 times negative 5. Which is 1. It'll be 4 plus 1, yeah. So, yeah, that's, or at least off of the calculations we got. So the final velocity of our second ball here is a positive 5 meters per second, which means it's going in the opposite direction that it began with. So that's our answer here. Now, let's double check that momentum. So our initial momentum should be this. So let's see here. So all my variables. So it would be 4 times 5. So that's 20. It would be 20 plus a negative. Be negative 6 times 5. So negative 30. So what we should expect here is negative 30, or sorry, negative 10 kilograms by meters per second. So meaning it's in the opposite direction as the motion. So then let's see what our final should be. Our final should be with the new velocities that we got. It should be 4 times negative 7 plus positive 5 times 6. So 4 times negative 7. It's negative 28 plus 30. Uh-oh. That's weird. What am I doing wrong here? 2 kilograms. Something's amiss. Because we should have the same momentum that we, at the beginning, that we do at the end. So remember, momentum is conserved. What am I getting wrong here? 4 times 5. Okay, yeah, 20. This is the momentum of 1 initially. Momentum of 2 initially. It's going to be 6 times a negative 5, which is negative 30. Okay, yeah. Okay. So then the momentum of our first object finally, and the momentum of our second object finally. So initial object is 7. It's going to be a negative 7 times the mass, which is 4. Yeah, which is negative 28. So I would expect then that this should be a positive 18, if this is correct. Which I can't get 18 with the 5 meters per second, because then it's going to be negative 5, or sorry, it's going to be positive 5 times the mass, which is 6, which is 30. I did something wrong here. Like something with the second object is not right. Because again, clearly, this has to line up. This has to line up. It's not to say that this has to equal to this. It's to say that the sum, so this would be a negative 10 kilograms by meters per second. This would be positive 2 kilograms by meters per second. So I'm missing something here. I don't think I gave you guys the wrong, did I plot out all those numbers in wrong though? So it'd be 2 times 4. I'm looking back at my calculations for the final velocity for object number 2. So looking at that again, it would be 2m of 1, m1 plus m2 times plus. I think I see it now. Yep, I think I see it. M1 it's right here. I wrote this down, but I plotted in backwards. I put M1 minus M2, so that's probably where I went wrong. So then it's going to be 2 times 4, 4 plus 6, times 5 plus 6 minus 4, 4 plus 6, So negative 5. Let's try that again. Okay. My bad, guys. So then we get, over here we get 4. And then it's going to be 6 minus 4 over 10 times negative 5. So then instead of plus 1, it's going to be minus 1, which is then going to give me not 5, but 3 meters per second in this direction. Okay, that's going to make a huge difference now. So looking back at this guy, so now the answer should be 3 meters per second. So we can keep this. This should be correct. So looking at this guy, it's not going to be 30. Now it's going to be 3 times, and a positive 3 at that, 3 times 6, which is 18. Now we've got it, yeah, negative 10 kilograms per meters per second. Now we have conservation of momentum. Now we have the correct units. So overall, long-winded way, a whole lot of calculations to say that the final velocity of our first object is negative 7, or I shouldn't put negative, 7 meters per second in the opposite direction that it began with. And then the final velocity of our second object is going to be 3 meters per second this way. Perfect. And this should be something we expect. We should expect that this is going to move slower after collision because it's larger due to its larger mass. Oh boy. All right, one more. So a proton with a mass of 1.01 AMUs is traveling with a speed of 4.5 times 10 to the 6th meters per second, collides elastically with a helium nucleus, which has a mass of 4.0 AMUs that is at rest. What are the velocities of the proton and helium nuclei after collision? Okay, and we're just going to use AMUs in place of kilograms. Okay, so we're just going to keep that. Okay, so let's check your understanding, number 7. So the mass of our first atom, we're going to say just mass 1.01. And remember, we're swapping out AMUs with kilograms. And it has a velocity initially of 4.50 times 10 to the 6th meters per second. And we're going to say it's just moving in this direction. And the mass of our second, specifically our nucleus here, our helium atom, 4 kilograms, which is at rest. So we're trying to find, like we've been doing, final velocity of our first atom, or the proton here, and then the final velocity of our helium atom. Okay, we're going to use the two equations properly. V1F is equal to M1 minus M2, M1 plus M2, 2M2, 1 plus M2, V2I, which we can ignore this because it's the helium atom is at rest. So M1 minus M2, so that's going to be 1.01 minus 4 over 1.01 plus 4 times the 4.5 times 10 to the 6th power. So that means that was 1.02 divided by 1.01 plus 4 times 4.5 times 10 to the 6th power. So I'm going to get this right here. So it's gonna shoot back pretty quick. It's gonna shoot back at, we're gonna say 2.69 times 10 to the let's see, 1, 2, 3, 4, 5, 6 to the 6th power meters per second in the opposite direction. Okay, so that's what we got for our final velocity for our proton. And then we're going to find the final velocity for our helium atom, which we're going to find by doing this. 1 plus m2 v1I plus m2 m1. Again, we get to ignore this because this is 0, so we're just not going to worry about that side. Because again, the velocity is 0, it's at rest. Okay. So 2 times 1.01 over 1.01 plus 4 all times the 4.5 times 10 to the 6th power. 2 times 1.01 divided by 1.01 plus 4 times 4.5 times 10 to the 6th power. And then we should get this. We should get 1.81 times 10 to the 1, 2, 3, let's see, 1, 2, 3, 4, 5, 6 meters per second this direction. Okay, and just to end it, double check that the momentum's correct. So the momentum of our first object initially, momentum of our second object initially is going to be 0 here. This guy is going to be 4.5 times 10 to the 6th power times 1.01. I'm just going to write out what it is, so it's going to be this big old number. So then P1F, P2F, so 2.69 times 10 to the 6th power negative, I should say, negative 2.69 times the mass, 1.01 going to be a negative 2716900, and then 1.81 times 10 to the 6th power times 4, which is going to be 7240234 minus 2700. And then putting these together, I get this. I get 4523100. Super duper close. We're off just by, it looks like we're off by due to some rounding, poor rounding at that really, but due to some rounding, we are only off by what is that, about 22,000, roughly 22,000. Arguably this is close enough. I know this seems pretty far, but it's close enough, relatively speaking. It's 4.5 million kilograms by meters per second. And oh my goodness, that is the Check Your Understanding super duper long video here, guys. Just remember, you can skip through to see all the answers here. And real quick, the answers for number 7 here again. Final velocity of our proton is going to be this right here, 2.69 times 10 to the 6th power meters per second in the opposite direction that it began at. And then final velocity of our helium atom is going to be 1.81 times 10 to the 6th power meters per second, same direction as our proton was originally moving. Okay, that is the video. If you still have any questions, make sure you get a hold of me.